So before we jump into explaining PageRank, as Google calls it, we should point out that the web graphs that we're looking at in this chapter are much smaller, obviously, than the actual internet. The internet itself consists of something like 60 billion web pages. And that's only the known pages. Obviously, it's probably even larger than that. But we're constrained by what we can write on a single page. And without loss of generality, we can use these examples to explain the basic ideas behind PageRank. And so, now to get into PageRank a little bit, Google really explains their idea, their notion of importance behind this, or through this concept known as a random surfer. And so the idea behind a random surfer is that you have a person who's going to start on a given web page, and the person's going to traverse the graph by typically clicking on hyperlinks that he sees, maybe at random. So when he starts at page A, he's going to choose between B, D, and E, and maybe he chooses page D. And then once he gets to page D, he's going to choose between G, E, and C, and then he goes maybe to page E. But then sometimes, maybe the surfer gets bored of the page he's on, and then he decides to just enter a random URL into the browser. And so then maybe he arrives somewhere like page F, and there's no direct link between E and F because there's no direct hyperlink, but maybe he just makes that jump there and just enters that page randomly, and so on and so forth. And maybe he follows the graph again. And so at any given time, there's a chance that he's going to follow the web graph, or he's just going to enter something randomly. So we can break down this random surfing process step by step. First, let's ignore the fact that the user might enter a web page randomly, and let's just look at the structure of the web graph itself. And so from any given page, we're going to say that the probability that he chooses a page that he's pointing to is inversely proportional to the out degree of the page that he's on. So what I mean by that is since A is pointing to 3 pages, A has an out degree of 3. And so in degree and out degree are different. In degree is the number of incoming links, whereas out degree is the number of outgoing links. And so to each of these pages, he has a 1/3 chance of going to B, 1/3 chance of going to E, and a 1/3 chance of going to D. If he was on page C, the only possibility he has is to go to page E, so that would be a chance of 1, since the out degree is 1. And just take another example, if he was on page D, there's 2 outgoing links, one to page C and one to page G, so the probability there would be 1/2 that he's going to go to either one. We can return back to our example and look at our web graph, and it turns out that the ideas of importance can be represented succinctly on using this web graph. So in each of the 4 nodes, we can represent their importance as a letter or as a variable. And so we'll represent W's importance as W, X's importance as X, Y's as little y, and Z's as little z, lowercase. And at each of the links, we're going to indicate the probability that the user is going to traverse to that other node. And in order to do that, we have to take into account the fact that there's a certain probability that the user is going to be on the page in the first place. And that's really the measure of the importance, is the probability that the person will be on a page at a given time. So the importance square of W, if it's 25%, or 0.25, means that there's a 25% chance that at any given time the user is going to be on W. And so then the probability that we're going to split off to X, or split off to Y, since that's an out degree of 2, is not just 1/2, but it's W over 2, since we'd have to be on W first before we'd actually take this link. So the probability that we're going to use this link is really W divided by 2. And the probability that we're going to use this link is also W divided by 2. And similarly, we can look at z, for instance, and say that the probability that we're going to use this link is 1/3 times the importance score of z, or just z over 3. This is also z over 3, and this is also z over 3. So what we want to do is we want to solve for what each of the values inside these nodes are, which are the importance of the web pages. Again, it's the probability that that random surfer is going to land on a given page at a given time. So the fraction of times that W will get hit in that random surfing process is W's importance, the fraction of times that X does, Y and Z, and so forth. And so we're going to choose to solve for these importance scores algebraically. And basically, in order to do that, we have to relate each of the importance scores to the scores on the incoming links, right? Because in order to get to page W, for instance, we would have had to have been on page Z before, right? Because Z is the only incoming link to W. So right away, we know that W has to be equal to the sum of what's coming into it, which is Z over 3. So the chance that we're on W is actually 1/3 of the chance that we're on Z. Now let's look at one that's a little more interesting maybe. Let's look at X's importance score. So X is going to be equal to the sum of the importance coming into him, and that is W divided by 2, since he has this link here, plus Z divided by 3, since he has this incoming link here. So X is equal to W divided by 2 plus Z divided by 3. If we look at Y, Y has 3 incoming nodes. It has one from W, it has one from X, and it has one from Z. And so Y's is going to be W divided by 2 plus, now X is going to spread half of its importance score here. Each of these are X divided by 2 plus X divided by 2. And then we also have incoming from Z as well, so plus Z divided by 3. And then the last one that we're going to look at is Z. And Z has an incoming link from Y, and Z also has an incoming link from X. So Z's importance score is going to be equal to Y, because the entire Y is spreading all of its importance to Z. So once we're on Y, we're going to have to click to Z, plus the importance score from X divided by 2, plus X divided by 2. And so you can see that these importance scores are all interrelated, and it's not just as simple as finding the in-degree of a node, because we're basically weighting the importance of a node by the importance of the nodes that are pointing to him. Because, for instance, if we have a node that's inherently important, and he's pointing to another node, well then, if A is really important, then B should probably be really important too. Because once we get onto A, there's a high chance that we're going to click B, especially if A doesn't have a lot of outgoing links to other nodes. So really, the importance score needs to be defined in terms of the importance score that's coming in from other links, which is in turn dependent upon the importance score that's coming in from their other links, and so on and so forth. And so we get a system of simultaneous equations, and we will see how to solve those simultaneous equations.